All right, so we're going to continue on with MRI instrumentation and equipment. So let's just go over what we discussed last time. So our MR machine is kind of like our Russian nesting doll, where we have several layers. And we have our main magnet, but then we also have our radio frequency source, which is our transmit coil, our gradient system, that we'll talk about more today, our image processor, and computer system, where we ultimately see our images displayed on our control console. We talked about what each of these do, and our main magnet, static magnetic field, once again, are aligning our nuclei into the high and low energy states. Our RF field is going to excite those nuclei and put them into the transverse plane, which is ultimately where our receiving coils are at to receive the signal. And our gradient system is designed for spatial localization or spatial encoding of the data. So we have all this data being collected, but we need to make sure that that signal gets placed into the correct voxel. So we have gradients on either side of the patient, right and left, which are our X gradients, our Y gradients in front and behind the patient, and our Z gradients at the head and feet of the patient. And ultimately what they're doing is changing the magnetic field slightly in a predictable linear fashion so that we can select a slice and then select a specific voxel within that slice. And then our imaging processor, which is really our fast Fourier transformation. Because we're going to be collecting this signal, we're going to be putting it in a place called K-space. And ultimately, we're putting it through a fast Fourier transformation, which will give us our image that we see on our computer console. We talked about magnetic susceptibility. We defined diamagnetism, paramagnetism, and ferromagnetism last time. Our gadolinium contrast, which one is that? Paramagnetic, ferromagnetic, or diamagnetic?
Paramagnetic.
Paramagnetic, slightly attracted. So our gadolinium contrast is paramagnetic. Ferromagnetic, we know that strongly attracted, but it also retains those magnetic fields even when that external magnetic field is removed. So that's how we create our permanent magnets that we have at different sites. And permanent magnets are great for claustrophobic patients, obese patients, maybe patients in a lot of pain that can't get through a particular scan, because those are our open magnets. I put them in air quotations there because they're not completely open, but they're not cylindrical, so they're a little bit better for those claustrophobic patients. And the material for those permanent magnets is usually an alloy, alnico, which is a combination of aluminum, nickel, and cobalt. And this is what they look like. And a good thing to remember is our flux lines for these type of scanners are not vertical. I mean, sorry, not horizontal, but they're vertical. So it's important to remember how the flux lines run on a permanent magnet. They're going to be running vertically. Our resistive magnets, they work the same as our superconducting magnets, but the resistance is still there. We're not putting our coils in the cryostat, which is filled with liquid helium, to reduce that resistance. So we can't get the field strength that we desire, but one cool thing about these magnets is you can turn them on and off. So at the end of the day, if you want to turn it off, you can. But it does require a constant power supply, so our operational costs are very high usually. And then we talked about our superconducting magnets, which we've gone over many times when we discussed safety and various aspects. All right. So we talked also about fringe fields and how they get bigger as our magnetic field strength gets bigger as well. So it's important that we retain our fringe field, usually within zone 4. And we can do that in two ways, by passively shielding our magnet or actively shielding our magnet. And passive shielding is when we're just placing steel plates in the magnet or even in the room walls to reduce that fringe field. And then any active shielding, that's where we're using another electromagnet and we're just almost applying a magnetic field in the opposite direction to reduce that fringe field. It's cheaper, it's easier to site the facility because it's not as heavy, so that's always the desired option. We also discussed shimming, and shimming, and what we're talking about there is making the field as homogeneous as possible, meaning that the field strength at the toes of the patient is the same as at the head of the patient, 1.5 Tesla or whatever Tesla strength you have. So we have to shim the magnet between pulse sequences because a pulse sequence is designed to change the magnetic field strength slightly. So you have that time you usually have to wait between pulse sequences when the machine is automatically shimming and getting back homogeneous. And we have, once again, two ways that we can shim, passive and active. With passive, it's really just these metal discs and plates placed inside the scanner. And then active, once again, we have another electromagnet that is applied in the opposite direction to improve the homogeneity, kind of even it out. And then we talked about RF shielding, preventing any random RF energy and RF sources like a radio station, monitors from equipment that might be stored in zone 3 from getting into our room. Because if that RF gets into our room, it might be at the same frequency that we're transmitting, and it will appear as an artifact on our image. So to do that, we line the room in copper. And it's called a Faraday cage to prevent any RF from getting into the room. And that's why we also have copper teeth on our doors, and usually copper that is lining the holes that allow the cables to pass from zone 3 to zone 4. So I believe we are here on gradient coils. All right. So gradient coils are used for spatial encoding. And we have those coils at the head of the patient, at the feet, in front, behind, and on the right and the left of the patient. Because what we're doing is we're applying a little bit more current into those coils to change the magnetic field slightly. And we change it in a predictable linear fashion. So here, we could say that this is the Z gradient, because if this is the head of the patient and down here is the foot of the patient, we're changing our Z gradient in a predictable manner. So if we apply more current on this end and then less on this end or in the opposite direction, it creates this uniform linear gradient. But if we do not have the gradients on at all in the Z-axis, this is what it looks like. And it doesn't change our magnetic field from the head to the feet. So we can do this in all three planes. And we'll start to get into what this slice selection, frequency, and phase encoding directions are. But usually when we change our magnetic field strength in the Z direction, that provides us with a particular slice. So we know which slice we're going to excite. And our phase encoding is usually the short axis of the anatomy, and our frequency encoding is usually the long axis of the anatomy. And when we start to talk about scan time and scan time equation, you'll see why. But for some reason, this diagram, they did it the opposite, where they had the long axis from A to P as the phase encoding, and then the frequency right to left, but it's usually flipped around. So this is how you can see how we're starting to encode that data. We're selecting a particular slice, we're exciting a particular slice, and then we're going to basically make a matrix out of that slice and encode the data. Remember, if we apply two gradients at the same time, we can create an oblique plane. So there are some terms that we need to know in terms of gradient strength and speed. These are also referred to as the gradient activation terms. So you've seen this diagram before because we had to know this for safety. And the most important one in terms of safety is the slew rate. But let's define these again because this is going to be on this exam as well. But our gradient strength is also referred to as our gradient amplitude. So how high that gradient is turned on. How steep or strong a particular gradient is. And this is measured in milliTesla per meter, so field strength or strength of the magnet over a distance. Or Gauss per centimeter. And the conversion is 1 Gauss per centimeter equals 10 milliteslas per meter. And our next term, rise time, we can use the same diagram, but it's the time it takes in microseconds, because this is happening very fast, to get up to our gradient amplitude, or our gradient strength, maximum strength. So the time it takes for a given gradient when it's not turned on, so we haven't even turned this gradient on, it's got its baseline, 0. But then the time it takes from when it's activated until it's at its peak gradient strength. That's our rise time. So how quickly a gradient can attain a particular gradient slope. So the rise time affects how quickly the gradient can be switched on and off. And this in turn affects our scan time. So you're hearing that constant beating on the machine, and that really is those gradients switching on and off. And if it's happening faster, that means we have very quick rise times. And then our most important in terms of safety, our gradient slew rate. So this is not only the time it takes for a given gradient to reach its maximum amplitude, which is our rise time, but it's also what that amplitude is. So it's the gradient strength over the distance, and we're incorporating the rise time in. So the amplitude and the rise time measured together. So now its unit is millitesla per meter over seconds. So typically for most machines, you're kind of in this range of 70 to 120 milliteslas per meter per second, but it can go all the way up to 200. And 200 is usually our maximum slew rate, and that's regulated by the FFT A. So how strong it is at peak and how quickly it gets there. That's really what our slew rate is. And then our duty cycle. So this is usually expressed in terms of a percentage, or it can also be in terms of time, seconds or microseconds or even milliseconds. So that's the percentage of the time that the gradient is permitted to work. So as the slew rate increases, we also have a direct relationship with the duty cycle. And then heating also increases with the increase in the duty cycle. So going back to the original diagram, you can see here how everything is kind of broken down. So our gradient strength is really kind of how we increase above our threshold. And then you have your maximum amplitude or maximum gradient strength at the top. The rise time is how quickly that gradient is turned on until it reaches maximum amplitude. That's our rise time, and that's in microseconds. Once it's turned on, we have like a positive lobe, and as it's being maintained, that's our duty cycle. That's the time contributing to their duty cycle. So it can be a percentage of all this that's going on, or you could just think of it as in terms of microseconds. We also have the fall time when we turn off that gradient and it goes back down to equilibrium. But then right here, what do you think this is right here? Is this fall time or rise time?
Rise time.
It's rise time, but you're just going in an opposite direction. Okay? So you could label this as well as rise time, but you're just going in the opposite direction. Because these gradients are constantly going back and forth in the positive iteration and a negative iteration. And then it reaches, once again, another maximum amplitude, but it's in the negative direction. And then the time that it just kind of is on, that's our duty cycle. And then you turn it off, and then it falls back down to equilibrium. Okay? All right. So let's talk about these RF coils a little bit more. Our RF coils are designed to excite our hydrogen nuclei, and yes, they heat our patients up, right? They're putting energy into our patients. They happen to be the closest to our patients, and that's why burns are an issue, because that transmit coil is closest to our patient. The coil that's already built into the scanner is referred to as the body coil, because that is transmitting and it is also receiving signal as well, sometimes. But it's mainly used as resulting of transmitting. We put other coils on the patient to receive the signal. And those are strictly called receiving coils. But some scanners have these other coils called TR, or transmit-receive coils, where those coils are going to transmit and receive the signal, and that body coil that's surrounding the patient in the scanner is not going to be activated at all. And that's good in terms of if you have a patient with some kind of implants. So say you're scanning the brain and the patient has like a pacemaker. If you have a transmit-receive head coil, you're going to only transmit RF energy to the head and not to the rest of the body. So you don't have to worry about that device heating up and getting a resonant burn. Okay? So it will transmit with that coil and receive it. So those are called transmit and receive coils. This is a reminder that the body coil is really just designed to transmit, and then if you just lay a coil on the patient, that is designed to receive our signal. We have several different types of these coils. The one for most brain scans is called a Quadrature coil. This is where we have two receiver coils perpendicular to one another. And due to its design, we actually get an increase in signal coming from that patient. And it gets its name because our signal actually increases by 40%. 40%. Signal increases by 40%. And it increases by 40% because we're capturing two free induction decays. So this coil is receiving a free induction decay, which ultimately is signal. And this coil is also receiving a free induction decay. So with two coils designed to receive two and free induction decays, we get an increase in signal by 40%. So most head coils are designed in this manner. Another design is called phase array coil. This is where you have, like for spine work, where you have one long coil. It seems like one long coil. But it's actually broken up into smaller little surface coils as you go along. Okay? It's not just one huge coil kind of collecting everything. Okay? So what's good about this is you can kind of activate sections of this phased array coil. So most spine phased array coils are designed in a way where if you just want to image the C-spine, you activate just sections 1 and 2. Okay? Because you remember that body coil is surrounding the patient completely. So you're transmitting energy into the patient wherever that body coil is over top of. But if you're just receiving signal in a very specific area, that's beneficial because you're only looking at that body part. But if you happen to accidentally activate some of these other coils, we'll get to a unit called artifacts. The signal coming from this part of the patient's body can actually wrap into our image. And that's called wraparound artifact. So you want to be sure that you're only selecting the coils located near the area you're scanning. And on your Siemens scanners, you probably saw maybe some of the text hit those little sidebars that are on the image. Those are your receiving coils on a phased array setup. But if you have like a total spine study where you have to go from the C-spine to the T-spine to the L-spine, it's pretty cool. You don't really have to change out any of the coils. You just have to select different ones. So it's also beneficial to have smaller coils receiving than just one large one because you get an increase in signal and it allows you to cover more area. So it's best of both worlds. Smaller coils are actually better than just one large one in terms of signal to noise. And then you get the coverage as well. So most spine coils are set up in this way. And with Siemens, they're already built into the scanner. So they're like that cushion that's on the Siemens scanners, that is the coil. Like if you want to take that coil off, you basically have to take like the cushion apart. GE, sometimes you have to add an extra like coil on top of the actual bed. Yeah.
Is there always going to be 6 sections for the phased array, or is it just...
No, but that is kind of typical because that kind of gets you from the C-spine all the way down to like the sacrum. But it might be different, but I've seen 6 typically. Okay. And then you have all other types of receiving coils. So you have an ankle coil. You might have a dedicated coil for the wrist, the hand, the foot, the knee, the shoulder, right? You guys have seen all those coils in clinic. Those are receive-only coils, where you're just receiving signal. And to get maximum sensitivity, and what we mean here is the most signal with these receiving coils, it's important to get that coil as close to the body part as possible. So proximity to part should be minimal. So we need to get that coil really close to that body part. And it's nice when the coils are designed and shaped in the structure of that anatomy. The diameter, maximum signal with actually a smaller diameter. And that kind of goes back to our phased array. It's better to have smaller coils receiving the signal than larger coils. So smaller diameter, the better. And then if you can set it up so that you have multiple coils within that receiving coil, like with our quadrature, where they're perpendicular, and our phased array, where you have kind of sections, that always increases sensitivity. And a rule of thumb is, let's say you have a receiving coil, and just one of these flex receiving coils, and we're trying to measure the width of this receiving coil, and it comes to about 3 inches. How much in terms of depth do you think that receiving coil collects into the patient's body? It's only about half the diameter of that receiving coil. So if you laid a flex coil that was 3 inches in diameter on a shoulder, sometimes you'll have to use a flex coil instead of just a dedicated shoulder coil. Just remember, it can only receive signal about 1.5 inches into the patient's depth-wise. Okay? So sometimes you might have to put one on the front and one on the back. Okay, so just a general rule of thumb is whatever the diameter of that receiving coil is, the maximum signal it's collecting in terms of depth on the patient is half of that. So system hardware, let's talk about the gantry, the MR table, the operator interface, and the computer. So you'll see something like this at Showa. It's kind of a CT scanner, but you'll see this MRI has the same thing. Some even have TVs so they can watch shows and movies while they're getting scanned. So our gantry, that's really the actual magnet itself. You can also refer to it as like the bore. And our bore has the layers. And this is where that saying comes into play. Really good students choose MRI. So the closest layer of that Russian nesting doll is our RF coil, the inner layer. The next is our gradient coil, then our shim coil, and then our main magnetic field, B sub 0. So they'll ask on the registry, what are the layers of the bore or the gantry from the outside in or from the patient out? So just remember, from the patient out, it's really good students choose MRI. All right, our patient transport system. So some scanners, you're able to detach the table from the actual scanner, bring him into zone 3, move the patient over, and then bring the patient back in. Some do not detach. So if they do detach, you might have some kind of like hydraulic or mechanical lift. Like you'll see pedals sometimes. You'll just see like the up arrow, the down arrow. But usually when you kind of bring the table back in and hook it up to the scanner, there's some kind of lock button you have to push down so that it actually locks into the gantry so that when you hit the controls, it goes up and down. If you have any issue with that, that can really kind of screw up how just the software and the computer system operates. So if there's not a good connection there, that could be an issue. The table also usually provides the spots where the coils are actually plugged in. So your spine coil, all your receiving coils, that's where you plug them in. Okay? And all those coils, remember, you want to make sure they go down the middle of the patient in a very straight fashion. If you have some kind of barrier between those cables and the patient, the better. But remember, we never want to loop those coils when we're plugging them in and create that circuit. Most tables have like a minimum capacity and sometimes the maximum capacity. So you can see here, I think this is just supposed to be maximum capacity of 286 pounds, but each system is different. So make sure you know what your maximum capacity is for your table. Our operator interface, this is where us as technologists are selecting the protocols, manipulating the parameters, communicating with our patients via the intercom and the squeeze ball, turning on music for them. You can change if they have light in the scanner, if they need a fan. Some scanners even have different languages for breathing commands. And it could be touchscreen or mouse driven. Our computer, most MR systems use a minicomputer, must have large storage capacity, be able to do multiple calculations very fast. And the storage capacity is huge because there's so many images that come over in terms of MRI. It's not just 2 or 3 images like an X-ray, right? You have 4 or 5 pulse sequences, and each pulse sequence has like 20 to 30 images in it. And if you do 8 patients a day, you could be in terms of like 1,000 images on a day. And then most of the time, technologists don't clean out their storage for long periods of time. So if you start to see your computer lagging behind, it could be a storage issue where you're just kind of hitting that limit for that particular computer's capacity. So the computer houses the array and image processors. And it's important to know that this is just where it's housing the pulse control unit for our pulse sequences. And when we apply those RF pulses at specific times. So just that's kind of a common registry question. Where is the pulse control unit located? And what this pulse control unit does is, once again, it's really in terms of sequencing those gradients and those RF coils. When we apply the gradients, when we switch those gradients on and off, how strong we switch those gradients on and off. when we apply those RF pulses and at appropriate times. Also controls the transmission and amplification of RF, that's B sub 1. Monitors RF transmission to keep within FDA guidelines, our SAR limits. And it amplifies our free induction decay signal before sending it to the array processor for fast Fourier transformation. So those are all functions of this pulse control unit, which is housed in the computer. And then our array and imaging processors. So that free induction decay that's coming across, that's what we call raw data. Raw data that will be sent to the array processor. We don't need to know what these complex mathematics are going on in this fast Fourier transformation. But just know that the fast Fourier transformation is happening within that array processor. But what you do need to know is that it is a mathematical procedure that is converting signal in the time domain into the time domain to a complex number in the frequency domain. So you can see here how we're receiving these sine waves with that receiving coil. And that's over time. So we have signal that's going, has a positive pulse, a negative pulse. That's how we get that sine wave. And that, you think about it, that's because that's that vector in that transverse plane that's rotating around 360 degrees. So that's why it looks like that. And that's over time. But we need to actually, with our fast Fourier transformer, to convert that into frequency. What are the frequencies of these signals being collected over time? Okay. So we'll talk more about that, but that's the main thing that the fast Fourier transformation is designed to do. Take signal in the time domain and put it into the frequency domain. And then lastly, the image processor uses the data from the array processor to assign each pixel a shade of gray. Okay? So this is what it looks like coming from the patient's raw data. And it will actually be put into a place called K-space. So that's K-space too. The fast Fourier transformation takes this data, use complex math that we don't need to know, and it converts it into the MR image that we see on our computer console. Right. So here's a PDF document that's good for review. So I kind of drew the layers of the gantry in this regard, in this two-dimensional shape. Kind of show you it also kind of looks like an onion with all the different layers. So if we have the patient here, we have our RF coil, gradient coil, shim coil, and main magnet going out. This is what our superconducting magnet looks like in terms of just its main magnetic field. It's just a coil made up of niobium titanium that is wound, and then it eventually is connected back together. We pump a lot of electricity, a lot of electrons going through this coil. So current is supplied and voltage. And our Tesla strength is really determined by how much we pump in, how close those windings are together, and the number of windings that you have. Okay? And that ultimately gives us our magnetic field strength. The magnets that we have in the rooms, our static magnetic field is usually running horizontal, and you can see this right here is our fringe field expanding out. And I just denoted the 5 Gauss line here. Our shim coil is designed to make the magnet as homogeneous as possible, and its unit is usually in parts per million. So remember, the engineers, that's their responsibility. The moment that magnet's dropped off into the department or craned in or however they get that magnet into the department, they are designed, their purpose, one of their main purposes is getting that into a very uniform magnetic field strength. And it could be in the range of like over 30,000 parts per million when it's dropped off, and they have to use active and passive shimming to get it down to less than 4 parts per million before you can start scanning a patient. This is what it looks like for spatial encoding. So imagine our gradient magnetic fields look like this. So you have this solenoid coil right here, but then you have another layer. And what's happening is you're basically having, for the Z gradient, head to foot, you have one coil at the head and one coil at the feet. And to add to your field strength, you go with the same direction of current to increase the field strength slightly. So here I wrote B sub 0 plus whatever we are applying for the gradient. But to take away some of that field strength, you just apply that current in the opposite direction. And when you do that, it creates that uniform, linear slope. Okay? And at the middle of that slope is what we call isocenter. So that's that laser light that you send the patient into the center of the scanner. And with MRI, like if you're scanning the brain, you kind of select an isocenter right at the nasion here, or the glabella. And then the patient really doesn't move. Like in CT, you know how this patient moves through the scanner in CT. With MRI, you're applying these gradients to change the magnetic field slightly so that you can predict the precessional frequency of a certain area of the body. So the precessional frequency will also change slightly because of that Larmor equation, B sub 0, now with the gradient magnetic field. So you can excite a very specific slice. Okay. So what we do is we excite one slice, change the precessional frequency a little bit, and excite the next slice. And the patient doesn't move when you're applying these gradients, but you're able to get slice by slice without the patient having to move through the scanner. So just remember, we have these gradients being applied in all 3 directions. So that's why I put here the Y gradient is A to P, X gradient is right to left, and then our Z gradient is head to foot. And then these are just some reminders about our coils that are receiving the signal, and then some coils are referred to as transmit and receive coils, where like a head coil, if you want to transmit and receive, you can, and then you don't have to activate the body coil inside the scanner. And that's great for any time you have some kind of conditional device. Here, there's just a little something. Oh, I see that's an error. It's not times 4. Here, it's 40%. 40% increase in signal, not times 4. So use this document as a review. Also, you can watch one of my review lectures from years past for this unit, because we're not going to meet again for instrumentation and equipment. Okay? Your test for this unit is on Sunday night. All right? So use these documents, and I also created another Jeopardy if you want to run through that and play that as well. Okay. Yeah. Yes, x-axis is left and right. Let me go back to that. Or did I? X-axis left and right. Y-axis is A to P. So the x-axis is going to create your sagittal slices because it's left to right. And y gradient is going to create your coronal slices. Z gradient creates your axial slices. So I have this number right here. Where do you think I get this number? 42.57.
That's the Larmar frequency.
So that's the Larmar frequency. Okay. And at what Tesla strength? 1 Tesla, right? Okay, good. So this is the Larmar frequency at 1 Tesla. So at isocenter, you're going to get exactly 42.57 if this is a 1 Tesla scanner. Okay? As long as everything's shimmed appropriately. So what I'm saying here is this number is still going to be 42.57, but then when you apply the gradients, remember you're pumping current and clockwise down at the head, counterclockwise down at the feet, it creates this linear slope. And when that happens, you get the static magnetic field plus whatever that gradient slope is and how much it's changed it by on this end. But here, since it's now negative, you subtract whatever that gradient magnetic field is from B sub 0. Okay? And since this is in a predictable manner, you can determine what the Larmar frequency is going to be away from isocenter. So here, we're positive B sub 0 plus our gradient magnetic field strength. So I'm just going to give this a number, and I gave it 43.82. And that's more than 42.57, so it's changed it slightly because of that additional gradient magnetic field in a positive way. So now when I'm applying that RF pulse, if I applied that RF pulse at 42.57, you're going to excite those spins in that area. Okay? And usually what you do is you apply it with what we call a range. And that range is called a transmit bandwidth. So it's just a range of frequencies. Okay? But we aren't trying to excite in the abdomen. We're trying to excite over here in the neck. So now what we do is we tune our transmit coil. So now it applies it slightly off the Larmar frequency at 43.82. And when we do that, all those little hydrogen spins in this area get excited. Okay? And remember, due to resonance, if we don't apply it at a specific frequency, whatever's not within that frequency range, they don't get excited. So that's how we excite slice by slice, because we just change our transmit bandwidth slightly as we go down slice by slice. Okay? And remember, we can do this in the z-axis as well as in the x and y-axis. So that's what I was trying to draw with these additional little things here. So I just wanted to make sure I clarified that. Any questions? So remember, the test for instrumentation is due Sunday night. Image weighting is tomorrow night. You might have a ASRT module. I'm trying to think. An ASRT module that's coming up as well. But on Wednesday, where are we meeting and what time?
8:50 in the conference.
8:50 in the conference room, because we got to walk over there together.